Hello, everybody, and welcome back to BioSC 140. This is Lab 2 discussion video. So this is where we're going to analyze the data and learn about some of the physiological principles behind each experiment. Now, you should have already watched the experiment and data collection video for this section. If you have not, please go watch those before this. I'm going to assume you remember and know all the stuff from that video as I go through this. So the water bath, what do we do for this experiment? We have a water bath which keeps the temperature of water at 50 degrees Celsius. We then added in a bunch of water and we saw that the temperature of the water dropped down. Now, what's going to happen long term as we monitor the temperature of that water? Well, the water bath is going to detect that lowering of the water temperature. The water bath is going to detect that the temperature in the water dropped below the 50 degrees that it was set at. And so how is the water bath going to respond? The water bath is going to respond to this drop in temperature by turning on a heating unit. There's a few steps in this process. The water bath is going to have a thermometer which detects the change. So it's going to have a sensor, thermometer. That sensor or thermometer is going to then relay that information to a computing center, a central computing system that's going to decide what to do with that data. What the water bath is going to decide to do is it's going to say, that central computing center is going to say, hey, the water temperature dropped below where I want it to be. I'm going to turn on a heating unit. And so it's going to send a message to something that can affect change. Things can affect change we call effectors. So the effector in the water bath is going to be the heating unit. And it's going to turn that heating unit on until the water comes back up to 50 degrees Celsius. So we're going to see the temperature drop initially when we add ice to the water. And then we're going to see it slowly come back up to the 50 degrees Celsius over time as the heating unit heats up the water in the water bath. So how well does the water bath mimic human homeostatic control of body temperature? Well, what happens when your body temperature drops? What happens when you go outside in the winter in Tahoe and you get cold, or you jump into a cold pool? What happens when you drink a bunch of cold water? Just anything that pushes your body temperature down. How does your body respond? Well, your body's going to detect that change, and it's going to heat your body back up, either through shivering or by putting on more clothing or changing your environment, standing closer to a fire. Your body's going to do something to help bring that temperature back up to a normal level. So what elements of homeostatic control system does the water bath exhibit? So exhibit is it, we'll go to the next slide. I think it'll make more sense after this slide. So let's look at a few key terms and a few ideas, and then we'll revisit the water bath. So homeostasis, as I mentioned in the last video, homeostasis is the maintenance of a stable internal environment. Your body has a temperature. That temperature is going to be relatively stable. Your body has a set blood pressure. It's going to maintain a stable internal environment, homeostasis. Anything that's bolded and underlined, it's really easy to ask questions on the exam. It's really easy to write questions on. It's kind of like a wink, wink, nudge, nudge. Learn those terms. It's really important that you speak the vocabulary, that you speak the language of physiology. So homeostasis, maintenance of a stable internal environment. We're going to talk about that term every week for the rest of the semester. Set point. So homeostasis is the maintenance of a stable internal environment. Another idea that's related to this is the set point. The set point's the target value. Set point's the target value, the ideal value for a variable. So our set point in the water bath example is 50 degrees Celsius. That's what we told the water bath to be at. We said, hey, water bath, 50 degrees Celsius is what we want. In the human body, you can see in this graph that for most of the day, the set point for a human is around 37 degrees Celsius. When lights are off at nighttime, though, it drops to around 36 degrees. Daytime comes back, it's around 37 degrees. So set points can change. What are some other examples of the human temperature set point changing? Fevers. Fevers. So set point is the target value for a certain variable that you want to maintain, like temperature. During the day, your body wants to be at 37 degrees Celsius. During the night, your body wants to be at 36 degrees Celsius. When you get a fever, that target value increases to whatever your fever increases to. So set points can be altered. All right, so the set point in the water bath was 50 degrees Celsius. Now let's look at this idea of dynamic equilibrium, All right, so dynamic equilibrium. Where's equilibrium? Equilibrium is like balance, like everything's equal. Everything's kind of come to an end, right? Dynamic means like moving. So it's like moving and changing, but still all in balance. What does it mean when these two seemingly contradictory terms come together? Well, the definition on the slide is parameters fluctuate within a narrow range around a set point. So let's take the example of the water bath. So before we added the ice, we said it was at a constant 50 degrees. But if you had a thermometer that was sensitive enough to detect 1/1,000,000th of a degree changes, do you think it would have been perfectly flat at exactly 50 degrees Celsius? Probably not if you had a strong enough, accurate enough temperature thermometer. You would have seen that because of evaporation, because of heat transfer into the unit and into the air, the temperature of the water would have dropped down slowly, dropped down a little bit. 49.9999999, 49.99998, 49.99997. And then eventually it would have dropped low enough that the heating unit would detect it. And the heating unit would raise the temperature back up until the heating unit got turned off, then it would start dropping back down. The temperature would have actually fluctuated within a narrow range right around 50 degrees Celsius. It never would have been perfectly at 50 degrees Celsius for an extended period of time. It would have fluctuated up, fluctuated down, a little bit above, a little bit below, a little bit above, a little bit below. And that's exactly what happens around the set point in the human body. You have a set point for your blood sugar levels. Your body's going to fluctuate around that point. It's going to have a dynamic equilibrium right around that target point. Body temperature, you're going to have a dynamic equilibrium right around that body temperature. So temp is not always exactly 37 degrees Celsius. It fluctuates around it. Your body temperature might go up to 37.001 degrees and then drop down to 37, then drop down to 36.9997. It's going to fluctuate around that point, dynamic equilibrium. Antagonistic control. Antagonistic control requires two things. Bidirectional. So break the word down. Bi means two. Directions is directions. So two directions. So antagonistic control is control where you have two directions. And it has negative feedback. Negative feedback opposes change. So if you want to have your water bath right at 50 degrees Celsius and you put ice in and it starts to drop down below 50 degrees Celsius, negative feedback is going to resist that change below 37 degrees, and it's going to bring the temperature back up. In the human body, if your body temperature starts to drop, negative feedback is going to push it back up to 37 degrees Celsius or wherever your set point is at that moment. If you put on a parka and stand by a fire and you start to raise your body temperature, your body negative feedback will resist that increase in body temperature and bring it back down. Maybe you start to sweat. Your body will resist that change. So that's negative feedback. Negative feedback resists change. So antagonistic control is bidirectional negative feedback. It's going to resist change away from that set point. So body temperature goes up, it resists that change, brings it back down. Body temperature drops, it's going to resist that change and bring it back up to your set point. So bidirectional negative feedback. It opposes change and it always moves that variable back towards the set point. So all these terms are very important really for the whole semester. Think about these three terms and now compare them to the water bath. Compare them to the water bath. How is the water bath like a human system for homeostasis? How is the water bath different than the human system for homeostasis? Pause the video if you want to think about it a little bit. All right, so how well does the water bath mimic human homeostatic control? So it mimics homeostatic control because we have a set point like body temperature, 37 degrees Celsius. If our body temperature drops, it can oppose that change. It can bring it back up to 37 degrees Celsius. If the water bath, we put ice in it, can bring it back up to 50. So it's going to have some negative feedback to it. That's like the human system. If we, before we put the ice in, we set it to 50 degrees Celsius and we had some fluctuation around 50 degrees Celsius. We had some dynamic equilibrium at 50 degrees Celsius. Just like in humans, we have that dynamic equilibrium around our set point where it's not exactly at the set point, it kind of goes up and down, right around that point. How is it different? Well, I talked about how in your human system, in your human body, if you get cold, you can shiver, you can put on more clothes. I also talked about how if you get too hot, you can sweat. You can do things to cool your body off. Water baths do not have a cooling unit. Water baths, if you were to take a really big rock and put it in the middle of a fire till it got super hot, and then you put that super hot rock in the water bath, it would raise the temperature of the water in the water bath. And the water bath would not be able to respond. It would not be able to cool the water back down. The water bath has unidirectional, one-directional negative feedback. The human body has bidirectional negative feedback. Human system has antagonistic control. The water bath does not have antagonistic control. It has one-directional negative feedback. Now, what could you do? How could you change the water bath to make it more like a human system? What could you do to make a water bath have bidirectional negative feedback, like a human system? You could add in a cooling unit. Add in a cooling unit. So as cooling and heating unit becomes bidirectional. Perfect. All right, so in this experiment, this was the one where we took our resting heart rates, and then in class, we would have compared resting heart rates between people who exercise regularly and people who do not exercise regularly. So let's talk a little bit about heart rate. So heart rate, let's go to this slide. Heart rate is not homeostatically controlled. You don't have a set point for heart rate. What you do have is a set point for blood pressure, and heart rate is one of the variables that affects blood pressure. So heart rate is like a lever that you can use to change blood pressure. If your blood pressure goes up, you can slow your heart rate to bring blood pressure back down. If your blood pressure goes down, you can increase your heart rate to increase your blood pressure. You can see cardiac output is equal to stroke volume times heart rate. Cardiac output is going to be one of the factors when we talk about the heart. You're going to learn all about these variables. Cardiac output is a main variable for maintaining blood pressure. To maintain blood pressure, you need to maintain how much blood your heart's pumping. So heart rate isn't homeostatically controlled. It's blood pressure that's homeostatically controlled. And heart rate is like a tool that your body uses to affect blood pressure. It's one of a few tools that your body has to affect blood pressure. Now, is there negative feedback? Yes, there is negative feedback for heart rate. If your heart rate increases too much, your blood pressure is going to increase too much, and there's going to be mechanisms within your body to counteract that change. If your heart rate goes down too much, it's going to drop your blood pressure. Your body is going to respond with negative feedback, with antagonistic control, with bidirectional negative feedback. So heart rate does experience some negative feedback, but it is not a homeostatically regulated variable. There is no set point for heart rate. There's a set point for blood pressure, and heart rate is a tool that your body uses to change, one of many tools that your body uses to change blood pressure. Normal ranges between 60 and 100. So what do you think the results of this experiment are going to be? Are you going to have a higher resting higher resting heart rate in people who exercise regularly, or a higher resting heart rate in people who do not exercise regularly? Well, when you exercise, you work out your heart. You work out your cardiovascular system. People who exercise regularly have bigger, stronger hearts. They're able to pump more blood per heartbeat. Now, if you look at the total output of blood from your heart, there's two variables that come into play to calculate that. There's stroke volume, which is the amount of blood you pump per beat, and there's the number of beats per minute. If you increase the amount of blood you can pump per beat, you can have a lower heart rate and still have the same cardiac output. If you increase this variable by being an exerciser and having a stronger heart, you can decrease the heart rate variable while maintaining the same cardiac output. So usually it's the exercisers who have the lowest resting heart rate. But resting heart rate can have a few, genetics plays a role, size plays a role, sex and fitness all play a role in resting heart rate. Normal range is 60 to 100 for resting heart rate. All right, so pH is a measure of hydrogen ion concentration. A neutral solution has a pH of 7. Anything below 7 is going to be acidic, where there's a higher concentration of hydrogen ions than hydroxide ions, and basic is going to be the opposite. Your blood tends to be at about 7.4. 7.4 acidity is the ideal place for human blood. Anything below 7.3 is considered abnormal, pathological, and it's called acidosis. Acidosis. So it's underlined, it's a vocab word. Acidosis means your blood is below 7.3. Alkalosis means your blood has a pH higher than 7.5. Alkalosis means your blood has a pH higher than 7.5. Blood pH is a homeostatically controlled variable. Blood pH has a set point. Your blood's pH set point is 7.4. And your body has a lot of different variables, a lot of different tools to help maintain this 7.0 set point. One of those tools are buffers. One of those tools are buffer solutions. Buffer solutions reduce the amount of change there is in pH. Buffer solutions will, if you add in a bunch of extra acid, a bunch of hydrogen ions, buffer solutions will minimize the change in pH because of that. If you add in a bunch of OHs, buffer solutions will minimize the change in pH due to that. So knowing that buffer solutions help minimize change in pH, let's look back at this experiment, Fox 8.4a. This is the one where we measured the pH of pure water and added some hydrogen chloride, and we saw that the pH changed rapidly. It went down rapidly. We did the same thing where we measured the pH and added a base, pH went up rapidly. We then measured the pH of a buffer solution and added acid to our buffer solution, and we saw that the pH changed very little. We then did the same where we added a base to our buffer solution, and we saw that the change was very little when we added the base. Predictions, we got what we expected. Most people are familiar with acids and bases and how buffers work, and this is a very predictable result, I think, for most students. If you look at this sample data, there's really only one number that really jumps out, and that's this one down here, the 3 drops of NaOH. The reason why we got such a big jump with this one, was because that buffers tend to work in a narrow pH range. And once you get out of that pH range, they tend to not have a very large effect. So I don't know what buffer exactly we're using for this experiment, but that buffer tends to work right around that 7 pH, that 6 to 7 pH range. And once you get too far outside of that range, it has very little buffering effect. So buffers stabilize pH. They help resist change. If you have if you have a set point for your blood pH, and you do not want your blood pH to change away from that spot, what's a good way that your body could help maintain that set point? Have some buffers in your blood. Your blood has a lot of buffers in it, which will help resist the change in pH, help slow that change in, help minimize any deviation away from the set point of 7.4 for your blood pH. Different buffers have different capacity and optimal pH ranges. That's why we get such a big jump here, because the buffer that we use, we got outside of its optimal pH range. The major buffers in blood, bicarbonate. Bicarbonate is a major buffer in our blood. Hemoglobin actually has some buffering capability also within our blood. There's a lot of things in our bodies that produce acid. Producing energy in our bodies produces a lot of acid. So metabolic acids, metabolism is having chemical reactions happen, making energy. Lactic acid, pyruvic acid are all both produced in the energy producing process. We'll learn about that for test 2. And they release hydrogen ions into our blood. Bicarbonate helps minimize the amount of changes that we have due to the production of acids in our body. All right, so with that in mind, let's look at the next one. So effective exercise on CO2 production. So this is the one where we had 2 beakers. In those beakers, we made a solution that was slightly basic, and we added phenolphthalein. Phenolphthalein pink when we first start this experiment, and then we blow through a straw, we exhale into a straw, which blows air into the beaker until the solution changes color, and we measure the amount of time that it takes to turn the solution from pink to clear. We then exercise, and after exercising for 2 minutes or so, we exhale into the straw, and we measure the amount of time it takes to turn the solution from pink to clear. The solution is going to turn from pink to clear when we exhale, when the pH drops below a certain level. So let's look at this. So right here on this right side of the screen, you see this graph. This y-axis is pH, x-axis is time. At above an 8.2 pH, phenolphthalein is pink. At below an 8.2 pH, phenolphthalein is clear. So when we start the experiment, the solution has a pH of above 8.2. We finish the experiment when the pH drops just below 8.2. So metabolic acids. Carbon dioxide is, when it's dissolved in the liquid, makes the liquid more acidic. When we exhale carbon dioxide through that straw and into this solution, some of that carbon dioxide is going to dissolve into that solution, and it's going to make that solution more acidic. The more carbon dioxide we exhale, the more acid we're putting into the solution. The higher the rate that we exhale carbon dioxide, the higher the rate at which acid will build up in the solution, the faster the solution will change color. Now, are you going to be exhaling more? So the more carbon dioxide you exhale, the faster the solution is going to change color. Are you going to be exhaling more carbon dioxide when you're resting or right after exercising? You're going to be exhaling more carbon dioxide right after exercising. When you exercise, you use energy. You need to produce more energy. Carbon dioxide is a byproduct of energy production. It's a byproduct of energy production. And so when you exercise, you start using more energy, so you produce more carbon dioxide. As you produce more carbon dioxide from that energy production, you exhale more carbon dioxide. As you exhale more carbon dioxide gets absorbed into the solution. As more carbon dioxide gets absorbed in the solution, the faster the pH drops and the faster you see color change. So you will have a color change faster after exercising. Perfect. All right, so this next one probably has the point that is the most confusing for students. So pay close attention to this last experiment. And I'm going to point out exactly why students have trouble with this final experiment. So let's review what we do in this experiment. So in this experiment, we measure normal respiratory rate. Then we have the person hyperventilate for 4 or 5 breaths like this. And then we measure their breathing rate again afterwards. And do you think that their respiratory rate is going to go up or down after they hyperventilate? Well, let's look at this. Normally, so carbon dioxide, I'm going to give you a little hint. Carbon dioxide is the strongest, it's the variable that has the most impact on your desire to breathe. Carbon dioxide levels in your blood is the variable that has the strongest impact on your desire to breathe. I'll repeat that again. The variable that has the strongest impact on your desire to breathe is the level of carbon dioxide in your blood. When you breathe, normally you exhale carbon dioxide. You breathe in oxygen, your cells use oxygen to produce energy, and the byproduct is carbon dioxide. So carbon dioxide is a byproduct of producing energy, and you exhale to get rid of carbon dioxide. Normally, the breathing rate matches the rate of CO2 production. You produce CO2 at a certain rate, you exhale CO2 at the same rate. You produce CO2 at a certain rate, you exhale CO2 at a certain rate. When you hyperventilate, you exhale more CO2 than you normally do. So when you hyperventilate, you exhale more CO2 than you normally do. If the rate of CO2 production stays the same, so the amount of energy you're producing stays the exact same, that variable doesn't change. The only variable that changes is that you eliminate more CO2. You expect your CO2 levels to drop. This would decrease blood CO2, which would decrease your desire to breathe. So if the only variable that changed was that you eliminated more CO2, you would decrease your respiratory rate, you would decrease your desire to breathe. But that's not what we see. That's not what we see often in class. What we see often in class is that after hyperventilation, some students actually have a higher respiratory rate. So why would some students have a higher respiratory rate even though they're hyperventilating, which is eliminating more CO2? So I want you to think about rates. The rate of CO2 production and the rate of CO2 expulsion from your body, elimination from your body. If you make the rate of production unchanged, but you increase the rate of elimination, you should decrease the amount of CO2 in your body and decrease your desire to breathe. But what if you increase the rate of elimination, but you still increase your breathing rate, you still increase the level of CO2 in your body? You must have an effect on the production also. The act of hyperventilating uses energy. The act of hyperventilating requires the use of energy. Hyperventilating will increase the production of CO2, and it will increase the elimination of CO2. In some students, it's usually like 50-50 in class. In some students, the amount of energy that they use to produce, the amount of energy that they use to hyperventilate will increase the rate of CO2 production to a greater extent than the rate of elimination from hyperventilation. So in some students, the rate of CO2 production goes up higher than the rate of CO2 elimination. And this would lead to higher CO2 levels within the blood of that student, which higher levels of CO2, higher breathing rate. So this is why this is the hardest part for students to get, but don't worry, we're going to get this. If you have any questions, email me, let me know. I'm going to try to make this as simple as I can. Normally, you have two variables, two rates that are in balance: the rate of CO2 production and the rate of CO2 elimination. When you hyperventilate, you increase the rate at which CO2 leaves your body. But you also increase the rate at which you produce CO2. If you increase the rate at which you produce CO2 to a greater extent than you increase the rate at which you eliminate CO2, CO2 is going to build up in your body, respirations are going to increase. If through hyperventilation, you increase the rate of CO2 elimination higher than you increase the rate at which you produce CO2, you will eliminate CO2 faster than you produce it. Respiratory rates should go down. It's that duality. It's that thinking about rates that is difficult, that takes some thought for some students. Look back over the slides, re-listen to the last 3 or 4 minutes of this lecture, and if you still have questions about this, let me know. We'll go over this, we'll get through it. So that is the #1 spot where students run into issues. One last question, why would rebreathing into a paper bag help with symptoms of hyperventilation? So we've all seen this before. We've seen the movies, maybe it's happened to you, where you're getting on an airplane and you're really nervous about flying. You're scared of flying and you start to hyperventilate. You start breathing really fast. Now, what do people stereotypically do when they start to hyperventilate before getting on the plane? They breathe into a bag. They breathe into a bag. Why would this help? Well, it's going to help because it's going to slow the elimination process of CO2. When you breathe into a bag, you're going to breathe that CO2 right back into your body. And so it helps maintain CO2 levels. If you hyperventilate, you could exhale more CO2 than you produce, throwing your body out of balance, making you dizzy. If you breathe into a bag, if you rebreathe into a bag, it can help maintain those CO2 levels. All right, if you have any questions, please reach out to me. Have a great day, everybody.